the reason why gemstones are so precious is because of their imperfections. And the imperfections are based on the transition metals, contaminant in these gemstones. Okay, so what makes an emerald green or a ruby red or an amethyst blue? It has to do with the transition metals. And so here we are. These are different gemstones. And corundum is nothing more than aluminum oxide, and it's colorless, and it's pretty much worthless. But if you spike a little bit of chromium into the aluminum, then guess what you have? You have ruby. If you put a little bit of manganese for the aluminum, not in all the aluminum oxide, but just in a few spots in that mineral, then you have amethyst. If you put a little bit of iron contaminate in replace of aluminum, then you have topaz. So it's these materials that are colorless that gives rise to the different colors that we appreciate, that makes a worthless mineral priceless. Okay, so that's what crystal field theory is. In fact, the word crystal field theory was based on the fact that it explains it explains how crystals have their color. Okay, so that's a theory that we have. So I'm going to show you this movie real quick, and it sets the stage for what crystal field theory is about. So I'm going to go back to my computer here so that you guys can see that. Okay, I think we are good to go. So let me go ahead and play that, and then play that.
Crystal field theory explains most of the properties of complex ion bonding. Ligand field theory is actually MO theory applied to complex ions and is only briefly considered in these tutorials. The idea of crystal field theory is that the ligands approach the central atom and create a local crystal-type field, and this affects the d orbitals of the central atom. Transition metal chemistry is dominated by the d electrons that can occupy the 5d orbitals. Here is shown the 5d orbitals of the free central atom, also the 5d orbitals in the tetrahedral field and the 5d orbitals in an octahedral field. For a free transition metal, in the absence of any crystal field, the 5d orbitals are degenerate, which means that they all have the same energy. In an octahedral field, 6 ligands approach, 2 along the plus and minus z-axis, 2 along the plus and minus x-axis, and 2 along the plus and minus y-axis. When a ligand encounters a lobe of the central atom's d orbitals, it raises the energy. Hence, the dz squared and the dx squared minus y squared orbitals, which lie along the x, y, and z axes, are raised in energies, whereas the dxy, dyz, and dxz are out of the way of the ligands and are of lower energy. In a tetrahedral crystal field, 4 ligands approach along opposite corners of a cube, forming a tetrahedral crystal field. In this case, the dxy, the dyz, and the dxz orbitals are raised in energy, whereas the dx squared minus y squared and dz squared orbitals are lowered in energy. In an octahedral crystal field, we say that the d orbitals have an octahedral energy splitting, and we denote this by a capital delta with a subscript oct. The tetrahedral splitting of the d orbitals is opposite to that of the octahedral splitting. Also, the tetrahedral crystal field only involves 4 ligands, whereas the octahedral crystal field involves 6 ligands. Hence, the tetrahedral splitting is usually less than the octahedral splitting. For the same type of ligands, the tetrahedral field splitting is equal to 4/9 that of the octahedral splitting. Note that as these splittings increase, if possible, the upper electrons fall down to the lower states. These two different electronic configurations are called high and low spin complexes. The reason complex ions display such an array of colors is that the crystal field splittings lie in the visible spectrum. Light passes through a solution of complex ions, which absorbs the light specific to that type of splitting, and the electrons jump up. What we see is the light that gets through and is not absorbed.
So let me go back to the PowerPoint here, okay? Because I know that was a lot of information. So I'm just going to continue where this thing left off. Again, crystal field theory has to do with how the ligands upset the d orbitals in the metal. When it upsets the d orbital, so it causes something called a perturbation, and it causes the energy to differ, then it causes a phenomena in which the energetic field around the metal is altered. Okay, so that's what we mean by crystal field theory. So here is an example of the metal and the ligand, and the ligands are contributing their electrons to the d orbitals. There are 5 d orbitals. There's the dxy, dxz, dyz, dx squared minus y squared, and dz squared. Okay. So these 5d orbitals, depending on how the ligands interact with it, are either going to be raised in energy or lowered in energy. And that's important because it explains why we have different colors. So this right here forms a bond with a d orbital. So let's take a look at what happens. We basically have the ligands, and let's say we have 6 ligands and a metal. Separately, they're going to have this amount of energy. But when they come together, they actually want to form a bond, so their energy is lower. But that's when you form a complex. But as you push those ligands closer to the nucleus, then the complex gets sort of destabilized. So it goes up in energy. Okay. Now, as the ligand starts to interact with each of the 5 d orbitals, remember there are 5 d orbitals, dxy, dxz, dyz, dx squared minus y squared, dz squared. As each ligand approach these orbitals, then these orbitals are going to get perturbated. That is, their energy is going to differ. And that's the splitting that we see right here. Okay, that's a splitting. That splitting is important because that splitting gives rise to something called magnetism and the wavelength of light or the color that particular chemical is going to have. So the way we can see which orbitals are going to be affected is this is an octahedral field because we have an octahedral geometry. Octahedral geometry is basically got 6 ligands in the x, y, and z axis. And as these ligands start coming in each one of these axes, it's going to affect some d orbitals more so than others. In fact, it affects the d orbitals that are pointing directly along the x, y, and z plane. And which orbitals are those? It's going to be the dz squared, which has orbitals along the z-axis, and it's going to be the dx squared minus y squared, which has orbitals around the x and y-axis. These orbitals lie directly on those axes. Which orbitals are not going to be affected? The orbitals that are not going to be affected as much are these orbitals right here. You see how those orbitals are pointing right between the axis? That one would be dxy. Okay. This one would be dyz. So those orbitals are not going to be affected as much. It's only the orbitals that are pointing directly on the ligands that are going to be affected. And so that's how you get this splitting pattern. That's why you have this splitting pattern in which these dxy, dyz, and dz squared, in which the orbitals point between the ligands, are lower in energy compared to these orbitals which points directly at the ligands. And so what we have is a 2-3 split. A 2-3 split. If you play basketball, it's like a 2-3 zone. Okay. So why is that important? Because now what you have is d electrons. Okay, depending on how many electrons you have, what you will see is that the electrons are going to first fill the lower energy orbitals. That would be a D1. That would be a D2. That would be a D3. Remember we talked about D1, D2, D3. That's how many electrons in the D orbital. And then on the fourth one, you could either put it up here or you can pair it down here. So that's what is involved in crystal field theory. So the splitting here is important, and this splitting is unique for octahedral. Okay, and that's because in an octahedral field, you have 6 ligands coming in, and these are the ones that are mostly affected. In a tetrahedral field, what happens is that a tetrahedral, the ligands come in on the sides. They come in the sides. And so what happens is that these ligands are going to be the ones that are most influential by the ligands, that these orbitals right here are the ones that are going to be disturbed the most. And so for a tetrahedral field, it's actually the opposite. It's going to be 3 on top, these 3 on top, and 2 on the bottom, these 2 on the bottom. And that's what you saw in the movie. Okay, so that's your octahedral field, and that difference right there is delta. And that delta, that spacing between the two series of orbitals, is going to depend on what ligands you have and what metals you have. Okay, so let's take a look at, again, these are all octahedral field. Let's say that our ligand is fluorine. Well, fluorine doesn't interact very well with the metal, and so it doesn't cause that much perturbation, which means that this splitting right here is small. When you get to water causes more disturbance on the d orbitals, so you have a larger splitting. And then you have ammonia, which even gives you a larger splitting, and then you have cyanide, which even gives you a larger splitting. Why is that important? You guys remember from quantum mechanics that when an electron is in the ground state, okay, it can be promoted to an excited state. And then the color that you see is when the electron relaxes back down to its ground state. Well, that's exactly what's happening here. You have an electron in the ground state, and then if you shine light on these things get excited to the higher energy d orbital state. And guess what? These gaps right here, this gap, this difference, that falls within the visible spectrum. Why do you think transition metal compounds are highly colored? Okay, iron is sort of yellowish, copper sort of bluish, you get green, you get red, and things like that, whereas organic compounds are not. Organic compounds are generally white or opaque. They have no color to them. Well, the reason why transition metal compounds are highly colored is because this d orbital splitting is exactly within about 400 nanometers to about 900 nanometers, which is exactly the wavelength of light that we can see as colors. Okay, that gap right there is in the visible spectrum. And so we can appreciate when the electron goes to an excited state and then relaxes back down to the ground state, because that photon that is emitted, we can sense. So these gaps right here, it depends on the ligands. And those ligands, uh, that gap is dependent on the metal. Higher oxidation state, meaning that it's got a higher charge, gives you a larger gap. Ligands, based on the spectrochemical series. Spectrochemical series is just a series of ligands in which these give you the largest splitting, this gives you the smallest splitting. You find this in the appendix of your book, of your lab manual, as well as in the textbook. Okay, the gaps are larger going from left to right. Look at cyanide. It's all the way to the right. It gives you the largest splitting. Fluorine's all the way to the left. It gives you the smallest splitting. So that splitting will also give rise to what color these chemicals are. Okay, so when you have D1, you put an electron there. When you have D2, you put an electron there. The electrons are going to the low state. That's why we call it low spin. The electrons are spinning. It's going to the lower orbital. We say it's low spin. D3, we put one there. On the other hand, D4, that's where you have to decide. In a D4 configuration, let me just show you this real quick. You can put the electron on the high part of the d orbital, or you can pair it up. This would be called a high spin because the electrons are going to the higher orbitals. This would be called a low spin because the electrons are going to the lower orbital. And the question is, why would the electron prefer a high spin versus a low spin? And the answer lies with the fact that it costs maybe less energy to put it as a high spin. It might cost more energy when you pair it up. So what you have here is this, remember, is called delta. That's the energy that you need to pay in order to promote the electron to a higher energy state. And then here you have electron-electron repulsion. So that's called the pairing spin energy. Because when you put two electrons in the same orbital, they're going to repel each other. So that's an energy that you have to pay. So the question is the electron going to pay less energy when it's high spin or less energy when it's paired? And the answer lies when this delta is small. You see how this gap is smaller than this gap right here? Well, when this delta is small, then it will go ahead and pay the delta, the splitting energy, because that's not too much of a price to pay. On the other hand, when this gap is large, it costs too much energy to put the electron all the way up there. So it'd rather pay the spin pair energy, the pairing energy. So it's kind of like you trying to climb a little fence here. If there's a little fence there, you'd easily go over. And so you'd basically go to a high spin mode. On the other hand, if there's a huge wall, then it's very difficult to get over that. You would rather go around it. You'd rather be a low spin. So depending on that gap, which is influenced by the oxidation state of the metal and the spectrochemical series of the ligand, you're either going to be high spin or low spin, but not all elements are going to have high spin and low spin case. Let me just show you this. This is an example where here it's high spin, here it's low spin. And notice the gap. And notice that these ligands are also different. One is fluorine, so you have a small delta. One is cyanide, so you have a large delta. So let's take a look at these real quick. In D1, it's always low spin. You have no choice. D2, it's always low spin. D3, it's always low spin. D4, you now have a choice. It can either be high spin or low spin depending on delta. D5, you also have a choice. It's either high spin or low spin, this is low spin down here, depending on delta. D6, you also have a choice. D7, you also have a choice. D8, there are no choice. Okay? Because 6 will go on the bottom, 2 will go on top. There, it's all going to have that same configuration. There's no choice between low spin or high spin. So for these guys right here, you don't have a terminology for low spin or high spin. It's only between D4 through D7 that you have that choice. Okay, low spin or high spin. And notice that whereas this high spin has 3 unpaired electron, this low spin has 1 unpaired electron. So that's where we have this concept called magnetism. When there are unpaired electrons, you guys hopefully remember paramagnetic. Depending on how many unpaired electrons you have more degree of paramagnetism. When you have 0 unpaired electron, like in this case right here, there's a D6 right here. There are no unpaired electrons there. It's called diamagnetic. Yeah, the specific value for delta, it's also called 10 dQ. It's measured experimentally. What you need to do is you just have to size it relative to another chemical. You don't have to worry about doing that calculation. And these things are going to vary from small gradually to large. When the ligands are weak field, that is, they're in the low side of the spectrochemical series, they're going to have a small gap. If they have a small gap, then the chemical's probably high spin. When it's a strong field ligand like cyanide, so there's a big delta, most likely the electrons are going to go to the lower state because it's too much to climb to the higher state. So that's going to be a low spin configuration. So when the gap is huge, it's a low spin case. When the gap is small, it's going to be a high spin case. And you see that a lot. And why is that important? Because again, the splitting gives rise to colors. Okay, I'm going to cover in this next 10 minutes how we see colors, and it'll explain beautifully why these things are highly colored. Okay, so why is ruby red? Why is copper ions blue? Well, you have to understand how we perceive colors. So these are the experimental data real quick, but how exactly do we see colors? And remember, the only thing, the colors that we do see are from red to blue. Outside of that, we see it as heat when it's beyond red, and it's ultraviolet when it's beyond blue. Okay, so you guys remember Roy G. Biv in grade school? That's the different colors of a rainbow. It's red, orange, yellow, green, blue, indigo, violet. I is indigo. So here it is right here. You can easily do a color wheel because it looks like this. And you guys should know how to do this. Red, orange, yellow, green, blue, violet. And indigo is in between blue and violet. Right in here. Okay. So basically that's what you see in this slide. Okay, how do we see colors? Well, when you see black, the reason why it's black is because when light hits it, all the different, remember, light is nothing more than the superpositions of the different wavelength of light or the different wavelength of colors. Here we see red, orange, yellow, green, blue, indigo, violet. And when it hits a black surface, all those wavelengths are absorbed and nothing gets reflected back into our eyes. And so the absence of these wavelengths is black. Hopefully you bought into that. When we see white, look at your screen, you'll see a white screen there, right here, white. It's because when light hits it, all the wavelength of light that hits it, all of it gets reflected back into our eyes. And so the superposition of the colors is white. Okay. Now let's take a look at how we see orange, a specific color. The way we see orange is when the different wavelength of light hit orange. All the other wavelength of light gets absorbed except orange, and orange is the only wavelength of light that hits our eyes. And so we see that particular object as orange. Okay, just look at an orange fruit or something. But more importantly, the other way we see orange, and this is the important part, is because if you look at the color wheel that I told you about, red, orange, yellow, green, blue, violet, orange is right here. The complement of orange is blue. Well, if blue is absorbed, and all the other colors except blue gets reflected back into our eyes, then we see that object as orange as well. That's a really amazing phenomena, okay? So if we see an orange object, it's either because only the orange wavelength of light hits us, or more importantly, this is especially true in spectroscopy, orange is absorbed and then the other complement colors hits our eyes. Then the absence of orange makes that object look blue into our eyes, okay? So why is that important? Because now you know, okay, now you know that if an object is yellow, if we see an object as yellow, then the color of light that was absorbed is, this should be ultraviolet, is the complement color, ultraviolet. If we see an object as red, then it's because the green light got absorbed. And so if we take a look at this experimental data right here, okay, these are experimental data. I'll go to this page right here. Here we see a compound. This particular compound, let me go back here. Oops, there. Remember, fluoride is a weak field ligand? That's a small splitting. If it's a small splitting, then the light that is going to be absorbed is going to be a low energy light. What is a low energy light? It's red. What is the complement of red? Again, get our color wheel. If you forget, sometimes I forget, red, orange, yellow, green. Complement of red is green. Guess what that color looks like when we actually see it? It's green. Let's take a look at oxalate. Oxalate's right in the middle. It absorbs yellow and violet. Yellow and violet's about here and here, and we see it as green because violet sort of is complement to green. But let's take a look at cyanide. Cyanide is a large split. That energy of light, because the gap is so huge, is going to be large. What are high energy light? That would be blue and violet. What is the complement of blue and violet? That would be yellow. That's exactly what we see. Okay. So I'm going to sort of stop there, and then I'm going to finish this off next time, then go into nuclear chemistry. But again, it's an amazing phenomena in terms of how crystal field theory explains the things that we observe. Okay. So I'm going to go ahead and stop there because I don't want to rush things, and then I have a lab in 10 minutes. But again, I'll review this next time so that you guys can appreciate it. The take-home message here is you should be able to explain magnetism and colors of compound based on crystal field theory. Okay.